Hello, I'm Johnny Pisano, and this is how to determine the rate law of a reaction using spectrophotometry. In this lab, we are asked, what is the rate law for the reaction between crystal violet solution and a hydroxide solution, and how can that be determined using Beer's law and spectrophotometry? To begin, you must set the colorimeter to 610 nanometers and use distilled water as a blank. The choice of distilled water as a blank will later be discussed. Now, for the concentrations of crystal violet you will use, you create a serial dilution for 5 concentrations, with the starting concentration being 25 micromolar. Find absorbance for each of the following concentrations. Once all the calibration curve data has been collected, you must create the data for the change in concentration of crystal violet when it is reacted with hydroxides at differing concentrations. First, add 8 milliliters of crystal violet to one graduated cylinder and 2 milliliters of hydroxide to another. Then, combine the reactants into the third graduated cylinder and mix with the pipette. Then, take the sample and add it to the cuvette. Then quickly apply it to the colorimeter and start taking absorbances based on time intervals of 30 to 60 seconds. This colorimeter should have been blanked with distilled water as well. Once all that data has been collected, repeat the steps with 1 milliliter of hydroxide and 1 milliliter of distilled water in place of the 2 milliliters of hydroxide. What you'll find as you record absorbances over time is that the absorbance will begin to decrease. As the reaction progresses, the solution gets lighter and lighter, allowing more light to pass through that was once previously absorbed by the colored crystal violet solution. Now onto the data that was collected. Here is the data of the calibration curve trial. As you can see, a line of best fit can be created from the data when put into a scatter plot. This line can determine at what specific absorbance what the concentration of crystal violet should be. Here, we track the absorbance of crystal violet based on its molarity. This creates a relationship between absorbance and molarity. Once we give an absorbance of crystal violet, we can then determine its molarity. This can be used later as we find specific absorbances over time. Here is the data for the first trial with 8 milliliters of crystal violet and 2 milliliters of hydroxide. Here is that data based on time and concentration. The relationship between time and concentration is not linear, as you can see a curve. This is important for later. Here is the relationship between time and 1 over the concentration. As you can see again, the relationship is not linear and it has a heavy curve. Here is the relationship between time and the natural log of the concentration. As you can see here, the relationship is highly linear, which will be important for later. Here's the relationship with 8 milliliters of crystal violet and 1 milliliter of hydroxide and 1 milliliter of distilled water. Once again, here's the relationship between time and the concentration. With a slight curve, it is obviously not linear. Here's the relationship between time and 1 over the concentration. Again, not linear as it has a curve. And here's the relationship between time and the natural log of concentration, which is obviously linear. Again, this will be important for later. Now, we must use this data to find the rate law for the reaction. Here is the rate law for the reaction. The question is, how was this found? First, we must find the order of the crystal violet solution. This can be determined by looking at the graphs and determining which one is linear. As stated before, the first order integrated rate law, or the natural log of the concentration, was the linear graph. This shows us that crystal violet is first order. This means there is a relationship between the rate and the concentration, but only when it is the natural log, indicating that it must be raised to the first power. The slope of this line is K prime, which we will discuss now. K prime can be determined by looking at the differential rate law once we find that crystal violet is raised to the first power. Since crystal violet is raised to the first power, and it is in a linear relationship with rate, everything that came before crystal violet is to be considered the slope. So if we put slope into one letter, K prime, and then set K prime equal, we get that K prime is equal to the rate constant times hydroxide raised to its order. And using this as a pseudo rate law, we can determine the order of hydroxide and the rate constant. Before we can do all that, we must determine the real concentration of hydroxide using the graduated cylinder. Because we added a highly concentrated small amount to a larger volume, we decrease the molarity, as molarity is moles over liters. Therefore, we must find the real molarity of each concentration of hydroxide. And using M1V1 equals M2V2, we can do just that. Now that we have the concentrations, we can determine the order of hydroxide. To do this, we must put one pseudo-rate law over the other using two trials. Because we know that K prime is the slope, and we have two slopes, we put the slopes over each other, and using basic algebra, we can determine that the order, or m, equals 2. So hydroxide is second order. Now we must find the rate constant, as it is the last thing in the differential rate law we must find. By using one of the pseudo-rate laws and plugging in m for 2 as we had previously solved, and then plugging in numbers from the first trial, we can easily find what k equals. We also must put correct units, which will be explained. Here is the final differential rate law for the reaction. As stated earlier, we must put correct units for k. Without k, the final rate would be in molarity squared, as we have 1 molarity to the first power and 1 molarity to the second power. So we must cancel out these molarities and put it per second, as rate is molarity per second. What the order of each reactant means is that for crystal violet, for every factor of 2 you increase the concentration, the rate is increased by a factor of 2. But for hydroxide, for each factor of 2 you increase the concentration, the rate is increased by 2 to the second, so the rate is increased by 4. Now onto the errors and limitations of this lab. The first limitation is using a colorimeter. Because a colorimeter was used, we had a limited selection of wavelengths that we could use to determine the absorbances. And because of this, some absorbances were over 1, which is improper because absorbance is a measure of the percent, and you can't have a percent over 100. To fix this in future labs, you should obviously use a Spec20 and determine the perfect wavelength to give just close enough to 1 without going over, at the highest concentration of 25 micromolar crystal violet. The second limitation was the blank used. The blank used for this lab was all distilled water. Distilled water works as both solutions are aqueous, so therefore there is nothing being missed. However, to reduce the maximum possible error, we could use hydroxide as the blank. However, it would be hard to do this in the calibration curve, as that means that we would have to put hydroxide in the concentrations, which would then react and give a skewed calibration curve, meaning that water for now will be the best blank. Finally, the last limitation is a lack of trials. In every lab, adding more trials increases the accuracy of the data. However, in our lab, we only had one trial for each test, and this led to outliers, specifically an outlier at time equals 450 seconds on the first trial. To fix this, simply do more trials of each test inside the entire lab. This will increase accuracy. How else can this data be found for different reactions? In a gas reaction, without a color change, one must, instead of using spectrophotometry, use changing in volume by attaching an elastic container to the reaction vessel. And using the ideal gas law, PV equals nRT, we can convert the pressure into molarity and concentration. Then, using the concentrations, we can use the integrated rate laws in the same way we used in this lab to determine the rate law. For a precipitate-forming reaction, we must instead put a marker on the bottom of the reaction vessel, then add the reactants and watch as precipitate forms. Once the precipitate covers the entirety of the marker, we must mark this time using a timer and determine at which times the reaction finished. Then, using the concentrations of the reactants and the integrated rate laws, we can once again determine the order of each reactant, following the same steps that we used in this lab. Thank you for listening.